If you share a house with some roommates, you certainly wouldn't want them snooping around your personal belongings. Well, because microcontrollers are becoming multi-tenant, you will face exactly the same type of challenge when using them. So in this talk, we want to present our TinyPART Toolkit to anybody that is susceptible to be using IoT devices or to develop some. We will show you how you can address this multi-tenant challenge by addressing issues related to memory isolation, software updates, and resource access control.
Welcome to TALK.CYBERCNI.fr.
Bienvenue.
Welcome to the 40th edition of Talk CyberCNI. So already 40 times that we informed you about cybersecurity and all the different facets this cybersecurity can have in your life. And today we have another super interesting topic, because today we go to the world of the IoT and we have a talk about software multi-tenancy of microcontrollers, enhancing security with the TinyPART Toolkit. And as you've already heard in the intro by Chrystel, this is about, you have IoT devices standing around that are measuring things, that are doing things, and in general, they don't have any access controls, they don't have multi-tenancy, and the talk will probably, at least in some part, also cover how you can add that later by having some intelligent software stacks. So, very nice that you're with us, and as always, we have the second screen. So we have the Slido. I'll just switch over to explain it to you again. So yeah, here you see the URL. It's not surprising. So it's talk40, and so if you go to sli.do/talk40, you have the question board. Don't hesitate to connect, because as you know, it's most interesting if we have lots of questions for afterwards. And also, even if you don't have a question at the moment, it's interesting to follow this board and to see what is happening there. What are the questions other people are asking? You can also upvote and downvote questions. And so it's a very good idea, as always, to connect to this. So today we have three speakers. It's also a first of having three people presenting, and it's great. So we have Chrystel Gaber received her PhD in computing systems from the University of Caen in 2013. And after working as a project coordinator and R&D engineer at FEAM, she joined Orange as a research and project coordinator. She's involved in several projects related to cybersecurity, IoT device management and certification, and serves as the French coordinator of the TinyPART project. Our second speaker today is Gilles Grimaud. Gilles Grimaud received an award from the French chapter of ACM SICOPS for his PhD thesis in 2001, and he was appointed a full professor at the University of Lille in 2009. His primary research interests include embedded systems, cybersecurity, and formal methods, with notable achievements such as the development of CAMI, a secure smart card operating system. He has contributed to numerous funded French and European projects, and he's currently a member of the TinyPART project. And the third with us today is Emmanuel Baccelli. And Emmanuel, he's a researcher at INRIA and at Freie Universität Berlin. And he's having previously worked at IT&T Labs and Micro-Optics Inc., Metro Optics Inc. He earned his PhD from École Polytechnique in 2006 and his habilitation from Université Pierre Marie Curie in 2012. And he's a co-founder of the Riot open source community, and his main research interests involve the Internet of Things, low-power software, security, and the design and analysis of network protocols and algorithms. And you know why I always tell you this at the beginning, not only to shine the glory on the people, but also to give you a context of who is presenting. And I'm super happy having you three with us today. And with that, I don't want to take more of your time, and would hand over directly to Chrystel to start with the interesting talk.
Hello, everybody. So, as you have seen in the trailer, sorry, I would put it like that. So, if you share a house with roommates, well, you wouldn't want them snooping around your personal belongings, but you would like to be able to share energy efficiency device and to save money. So you will face the same type of challenge, and we're going to discuss with you how the TinyPART Toolkit can help you in this challenge. So let's start from the beginning. The TinyPART project is a Franco-German project which started in 2021. We are 5 partners, 2 industrials, which are Orange and FISEC, and 3 academics, INRIA, University of Lille, and the Free University of Berlin. When we built the project, we observed that IoT device manufacturers had 3 types of needs. First of all, the marketing differentiator, which is to create a unique customer experience using personal services, um, which require a high flexibility of development. And that is complex to achieve for IoT devices because they are usually built with a monolithic block of code. And also, there is a concern for marketing that privacy is a selling point. So when you're selling highly unique user experience, you also want it to be really concerned about privacy, and you really want to protect privacy. A second concern is that development and security require time and extensive expertise, while companies often need to optimize their time to market. And finally, right now, the EU is strengthening its legal framework for cybersecurity. And there are some directives, such as GDPR or the Resiliency Act, which impose manufacturers and service providers to ensure that they provide sufficient measures to achieve privacy and security. So in this context, the advent of lightweight containerization solutions make the flexibility of deployments available for microcontrollers. But there are some also existing IoT security models that need to evolve because they need to adjust to this new reality, and some tools are needed to adapt to the constraints of microcontrollers, and these need to be created too. So in this context, the TinyPART main goal is to empower IoT manufacturers with open source and freely available building bricks that will help them build secure and private by design architecture in this new ecosystem of multi-tenant containers. So to illustrate this need and how TinyPART addresses it, let us imagine a freight container manufacturer which decides to expand its traditional market of containers standardized for ships, trains, trucks, towards the creation of small containers that are standardized for drones. And now the question for this manufacturer is how can they differentiate from competition and add value to their product? Well, first of all, the freight container manufacturer could add some tamper detection feature optimized to minimize communication with its cloud application in order to limit energy consumption. And he can do that with, for example, federated tiny learning. Secondly, the freight container manufacturer could also use containers to allow a drone delivery service to display the name, address of the recipient, or maybe some specific instructions that will improve the overall customer experience at delivery. Or it could also loan some resources to a third party. So all these extra features complexify the capacity of the freight container manufacturer um, and other stakeholders to comply with regulation, and specifically GDPR and the CRA. Um, So this is where the TinyPART toolbox enters in the picture. It is composed by 7 tools, out of which 4 will be presented today, namely PIP-MPU, Suite, Femto containers, and Tiny Container as a Service. In this project, we considered 2 threat models, Stride for security and Lindun for privacy. There are 2 threats that are out of scope. Well, denial of service and also non-repudiation. And because we specifically containerization technology adopted the threat model that was defined by Hack et al., but in the context of Docker and Linux. Um, and in this context, here you see a simplified version of the threat model. The TinyPART project does not address the threats number 2 and 4, which both correspond to some remote attacker that is attacking the container or the container runtime or actually the host operating system. Um, and also, we do not consider attacks that are from the host operating system towards the container runtime or the container. That's because both of these elements are the container runtime and the host operating system are part of the trusted computer base, and we are relying on some complementary methods, but that are not built in the project, such as secure boot or supply chain security, to ensure that both components are genuine and are behaving as expected. So now I will give the role to my colleague, Gilles, to present PIP-MPU and XIPFS.
Contribution of the project. Uh, One of them is PIP MPU, and the other is executing place file system. Mainly, I will focus my talk on PIP MPU. So, can you slides? Chrystel, can you press? Thank you. So, about PIP kernel. So, with PIP, we are speaking about very small. Oh, sorry. Did you hear me? But it's better. So, okay, I'm not earning you here, but I will try to make my talk. PIP is a very small kernel, a seed actually, focus on security. Our goal is to remove untrusted or trust in the software by a proof. A proof is far better than trusting something. When you have a proof, it's harder, let's say. We want to prove some critical part of embedded system, or for example, some critical part of the container in the previous example. So the question is how to prove some piece of software. First, we don't want to prove the hardware. It's not because hardware is safe. There is a lot of threat issue coming from the hardware, but we are not focused on this here. Well, it's other part of the project. We are focusing on software, and if we want to have some element of proof, we have to choose what to prove, because proving is hard. It's a lot of work, and so we will not be able to prove all the stuff for each embedded software. Usually, software is built as a stack, as explained earlier, and so we carefully will select which component is the most relevant for require a proof. So we can imagine that the security policy need a proof, or a cryptographic tool need a proof, but ultimately nothing can be proved before the proof of isolation. Why? Because if you put some proof software just in front of some unproved software in your stack, the unproved software can be malicious or just buggy and allow to change the software you have proved. So, okay, you have a proof, but this is not what is running on the hardware. So your proof is like nothing. So we will not focus our effort on anything on this slide. Can you slice yourself? With PIP, we are trying to prove that the box are safe. What I mean, if you have some software put in a box, we speak about a partition, a memory partition, it means that you're alone in your space and nothing else external from your component, your software component, can change your behavior. That's the main goal of, that's the very first thing to prove. Because whatever you prove, as I explained just before, it's nothing if you are not able that what is running is what you have proved. So we want to prove that the whole box is cannot be compromised. We want also to prove that the trusting computing based, the stack of software cannot be compromised. If you have planned to use some subcomponent, this is the one you are using. Nobody can change it and put something else in place. And most of all, we have to prove that our isolation software cannot be compromised by anything else. So this is the third element to prove. So, okay, we have three stuff to prove. And how to do that? How to make isolation between software? Okay, we will rely on hardware. Even in the smaller microchip, we will find some specific hardware able to make isolation between pieces of software. Usually on a server, on a conventional server, this piece of hardware is called memory management unit, and it provides a way to handle access control on memory when the microcontroller, when the microprocessor is requesting memory access in order to run a software, for example. But in TinyTARGET, the one we are focused on in this project, there is no memory management unit, but there is a memory protection unit. It acts as a man in the middle between the CPU and the RAM, and it allows to specify which part of the memory is readable, writable, or executable. So by a careful configuration of this piece of hardware from a software, we can manage isolation between software components. Slice, please. So we speak about proof, but what are we speaking about actually? We speak that proving software. It has been defined by Hoare in the 60s, and it means that we can provide a way to reason, to make some reasoning on software. So we are using a proof assistant, well-known proof assistant, which is COC, to make some proof with a computer. In the COC proof assistant, there is a language, functional language called Galina, allowing to implement some software function. But this functional language is far more complex, and is too complex to be used on a microcontroller. So we have selected a subset of the language called Galina C, which is just enough to specify some function who will be embedded, like the one who configure the memory protection unit. We also specify some hardware abstraction. Here I'm speaking about we need a specification of the MPU hardware, and so we can implement and prove a property like the tree property shown earlier, in order to say, okay, what we claim, we have a proof, and the proof is here, and the proof has been checked by a theorem prover. So in this way, we have a software proved who enforce isolation between software components. But we have to, okay, I lose the slide. But we have to make the proof, and the proof is actually challenging. For 2,000 lines of code, we have 100,000 lines of proof. And for 4 months of work on the software, we have 30 months of work on the proof. So it's a huge effort. That's why we will not make the proof of everything in an embedded system. We will focus on critical part, and the very first critical part is isolation. Thank you. So what we have now the hardware, which is an unproved part. Over the hardware, we have the PIP MPU protokernel, which is not a full-fledged operating system, and then we have nothing else. So we have made an effort in the TinyPART project to port the Riot operating system, a well-known operating system deployed in various microcontrollers, over PIP MPU. It's like porting Linux on an hypervisor. You know, it's the operating system is no more the critical part of the system. There is an underlying software enforcing security. And over that, we can deploy some application. Next slide. And the application can be placed in separate, can be seen as separate piece of software. It can be placed in partition, managed by PIP, with the proof that the application stored here are isolated from the kernel. And so the Riot kernel can upload post-issuance third-party software and run it in confidence. That's the goal. But in order to be able to do that, we have to manage software deployment. Next slide. So we need something which is not provided by the Riot operating system. We need a way to store in the flash memory of the microcontroller some third-party software sent after issuance of the hardware. So we need a file system, something like that, and we need in the file system a way to say, okay, this file is actually a executable binary, and we want to run it over Riot. So this is the goal of executing place file system, which allow to upload file and compile file, and then run as you do over Linux, for example. And using PIP, we can enforce isolation of this file and be sure that it's not compromising the underlying operating system. Thank you.
Second part, so now that we have like software, they're in different partitions. Well, there are a few still caveats, right? So there are bugs that are going to come up down the line that you're going to find out. You're going to have to adapt to new regulations, new standards that pop up pretty fast. And from a business perspective, you're going to have to be able to continuously innovate, right? Even faster than the way the period, the frequency at which you roll out new hardware. So this all calls for the need for software updates. Even if you have a software update mechanism, there are some caveats. So your updates is both a tool and something nice. It can also be an attack vector. So what if the update is laced with malware? What if the update is a mismatch and actually breaks your system? So you actually need some software update security mechanism. And there are even more caveats on microcontrollers where you have very stringent CPU and power consumption constraints. So if you're talking about security in this context, you're talking about crypto primitives, and if you have to, dedicate half of your memory and precious uptime to actually compute, verify a signature or something like that, this is something that you really want to know firsthand. So basically, we need generic mechanisms that are compatible with low power in that context. We can go to the next slide. Um, and another thing to figure out or to observe in this context is that the on microcontrollers software update is pretty, let's say, primitive state. So you all know about like how you update software on your phone, for example. Every time you have to update your, I don't know, WhatsApp program, you don't have to update everything on the phone, right? You just update this one application, which is maintained by a number of people, which are different from the Android or iOS people, right? So you have like this here case three, where you have multiple stakeholders and modular software update. But the dominant approach so far on these microcontrollers is the thing on the completely on the left, which is like pretty brutal. Well, like whenever you change something, you actually change all the software on the device, right? And so we that's the first thing we looked at. We can go to the next slide. And that we worked on a new set of specifications and standards called SUIT that is actually developed at the ITF, the Internet Engineering Task Force, which specifies a new architecture, some metadata, and compact serialization for IoT firmware update security, specifying some authentication integrity checks and actually more checks. And this is in the final stage of standardization. I gave the link here. And we can also go to the next slide. Uh, so, yep. This serialization is based on something called CBOR, which is an RFC. I give the number here, and the security aspects. So how to actually assign this metadata, which is formalized as a so-called manifest, and how to ensure its integrity, how to um, encrypt if it is wanted, the actual binary of the update. This is all specified using another standard called COSI, which is also designed to be very compact, so that there are less bits over the air on one hand, and on the other hand also uses less memory, less RAM on the device to be able to handle this type of data. And so there, I also give here the link for the latest specification. Yeah, we can move on to the next slide. And what we've been working on is, so not only from the specification side, but also on the implementation side. So we have provided the reference of implementation for the standard, which is integrated in this operating system called Riot, which Gilles already talked about. And so this is now available to use out of the box on actually thousands of different software configurations that are supported by Riot on dozens of boards that are supported by the operating system on various microcontrollers of the ARM Cortex M family. We can go on to the next slide. Yeah, and based on that, we made some performance studies on what kind of costs in terms of memory, in terms of energy consumption, in terms of also computation time for actually verifying that the update is indeed hasn't been tampered with, or is actually originating from who it's supposed to originate from, so the authorized party. Both for pre-quantum security levels, 128-bit security levels, and post-quantum equivalent levels. And what we have actually measured is like this cost of upgrading for 128-bit pre-quantum to 128-bit post-quantum. So on the one side, it was a positive outcome in the sense that we could actually verify hands-on that it is possible, even on these small devices, to actually upgrade to this type level of security. On the other hand, there's a hefty price to pay, both in terms of memory consumption on the device, RAM and flash, and or network transfers, depending on what kind of firmware updates scheme you employ. And so we make some conclusions as to and recommendations as what to use as of today. We can move on to the next slide. And so what's next on that? Well, for you can try it out. I gave the link here. So it's in the main branch of Riot, and as I said, like there are dozens of boards that are supported already, and so there are chances that your board is already supported. And for us, well, the post-quantum aspects are not a done deal. Like the NIST competition is still ongoing, even though if it was almost finished at some point, they restarted it, and so we're still working on that, obviously, and following that very closely. And we're also working on a Rust version of that in RELOS, which is a Rust version of Riot that we're developing. That's all I'll say on this topic. I have a second topic I'll talk about very quickly. So fed containers, and so we can go on to the next slide. So as I said, like this first case of monolithic software updates and single stakeholder is a little bit like brutal. And so we wanted to transition the microcontroller domain into like something more akin to what you know on other types of hardware out there that is connected to the network, which is like multiple stakeholders and modular updates. And so we can go on to the next slide. And obviously, we also had a threat model here. I think Chrystel already talked about it a little bit, but we wanted to be able to host on the fly, modify additional functions, a little bit like a function as a service on these microcontrollers, and also be able to upload like new debug and monitoring snippets on the running device connected to the network. But at the same time, we wanted to not open too many new attack surfaces. And so we wanted to make sure that whatever mechanism we design, we are resistant to malicious tenants and to malicious clients. So make sure that the tenant cannot escape from the sandbox of this small container, and that clients cannot perform install time attacks. Right? We can move on to the next slide. So what you might know of containers is like typically in the cloud you have some VMs, and inside your VMs you have some containers. And what we did here is like something a little bit like the opposite of that. So we have some very small virtualization on some adaptation of the eBPF instruction set VMs that comes from the Linux world, and some container like integration that encapsulate these VMs that can interact with a real-time OS. So we worked with Riot here via syscalls to allow it to interact with sensors and network services and things like that. And these things, these elements can be remotely over the air, can be managed remotely over the air via suite. So you can update these containers securely using the same mechanism that we described in the previous part of this talk. And the nice part here is that using this very small concept, the hosting engine for these femto containers, as we call it, is very small. So it's 1,000 lines of code. And so we were also tempted by formal verification here. And so we work with other colleagues who also used the COP Proof Assistant to verify fault isolation of the hosting engine that we use in Riot. We can move on to the next slide. So obviously we also made some performance studies here, and what we noticed is that compared to other types of prior work on virtualization and equivalents, such as MicroPython or small WebAssembly WASM engines that you could use to do something similar, you have a much smaller memory overhead. So instead of having to triple your memory footprint to have these containers, suddenly you just have to add 10% more memory footprint, and you have this continuation that's possible. What we also measured is that, for example, compared to something like WASM, we're a little bit slower in terms of execution. There's always an execution speed cost, so you're always difficult to be faster than native execution code when you're virtualizing, obviously. The question is only how much slower you are. So we're a little bit slower than WASM, but we're working on that. We can move on to the next slide. So yeah, in a nutshell, it's a nice alternative if you're looking for very, very small memory footprint overhead and still have some virtualization. The execution time penalty is not fantastic, but it's still acceptable. It's also integrated in Riot and on par with actual standards. There's actually a standard with that has just appeared with eBPF instruction set, and actually that is a good candidate for some proofs and isolation using pip NPU, the tool that Gilles was talking about. There are some limitations, however. So obviously, as I said, it's virtualization, so you have this speed slump. There's maybe the most stringent limitation here is the limited expressiveness of this of the logic that you can host in these things. So, for example, it's difficult to implement loops in there. So it's definitely not Turing complete what you can actually have inside these containers. So it obviously limits your the set of things you can do inside these containers. But for a lot of small functions, it's still very useful. Can move on to the next slide. So what's next here? Well, you could try it out. Again, there's an example I link to here. And for us, we're actually working on a project involving satellites, so nanosatellites that have to update their software while in the air. So they typically have a life of 4 or 5 years around the Earth, and during that time they have to modify their mission code, things like that. And so want to use these vector containers to actually modify just the mission code, and that's what we're doing in collaboration with University of Grenoble, Alpes, among others, and CSUG. I think that's all I had. So I can hand back the mic to Chrystel.
Yeah. Okay. So I will continue. So my colleagues who developed PPMPU and femto containers, well, what they aim to create is something similar to fortified self-contained islands. But in the context mentioned above, these islands may not be completely self-reliant. They may need to access to some resources, and we are on IoT devices, so there are some sensors, there are some actuators, maybe there are some other native functions that they may need. So we should more or less see them more like an archipelago, and they share some resources. And so it means that we need to have some way to see which is the legitimate container to use some resources at some point. And these are aspects that actually need to be fine-grained and defined at application level. So that's where Tiny Container as a Service comes. Um, we see that there is a business need to deploy some containers. So, for example, to personalize a user experience, or maybe to customize a firmware without managing too many firmwares in parallel. So, if we are relying on containers and you would like them to, for example, execute on a certain amount of time, well, you need to have some container lifecycle management. But in that case, if you have multiple containers running in parallel, um, how do you ensure that there is not a malicious container that is collecting data from another one that without the user knowing? Or how do you ensure that a malicious container did not change the configuration of a sensor while it's not expecting, which causes to poison some data that is sensed? And so that's why we need container access control. And as all of us mentioned, on microcontrollers, you don't have infinite resources. So you need some built-in optimized mechanisms to do that. So Tiny Container as a Service, we have three components actually at three stages. First of all, on the IoT device itself, we have an agent which uses manifests to that describe the rights that are allocated to a specific container. So this is exactly the same mechanism that you have on Android when you have an application that it needs to take a photo. Well, at some point there is a manifest that says this application will need to use the photo rights. That's exactly the principle that we followed to build our Tiny Container as a Service. Now, this agent it can communicate with a cloud platform because we have this container management system. So the application in the cloud is where we will collect the start containers, top container type of commands. And these will be sent to the IoT device through an edge gateway that is actually transposing a request from the cloud world, so typically HTTP, to IoT world, so typically co-op because it's efficient and it's made tailor-made for IoT devices with constraints. Um, so our context um, is the following. So here we take the use case that we discussed in the beginning. We see that there could be actually three stakeholders using this platform. So first of all, the freight container provider, because they have some code dealing with tamper detection, the drone delivery service provider, because they have some logic to deal with or display the address, or maybe deal with condition tracking. And also a third party that is totally independent from the delivery is a cartography service provider, but he's here to collect some data. during transport to make maybe a radio coverage map. There are several parts. The first part being all the syscalls that this particular container has the right to do. Then we declare what are the endpoints that the container has the right to use. So see that maybe a little bit like ports. What are the ports that containers have the right to use? And each we authorize the use of each endpoint separately. So there is an authorization code for each of them. And finally, there is a security body which contains some different checksums. So to guarantee the integrity of the container, the code, or even the data that is going with the container. If we focus on the tiny container as a service agent, we see that there are different parts and different functionalities. So first of all, there is an API that is exposed to the outside world, which allows to start and we have some abstraction of the runtime. So currently in Tiny Container, we support three types of container runtimes. We have WAMR, which stands to run WASM on microcontroller. We have RBPF that was presented to you previously, and we have JavaScript also. That's where we started from, a lightweight version of JavaScript. Um, and we actually use the adapter design pattern to make sure that we are able to expose the same API to command these different container runtimes. And then we have the firewall, which is in charge of dealing with all the rules to authorize system calls or the access to endpoints. We support multiple container running in the same time. And so in this image, you see that there are two containers. I think that needs to be noted is that we don't support running two different container runtimes at the same time. So if we have two container like that, it necessarily needs to be the same runtime, so WAMR, but we will not have a container running on WAMR and another one on RBPF. That's a choice that we made, but basically because we don't think that it's really going to be useful on IoT devices, and we are really constrained in memory. So if we want to be able to run multiple containers, well, it's better to save some time and have only container runtime. Um, this slide, I showed that the container has access to different type of resources. So the endpoints, it can represent either some remote resources. So for example, we want to send some collected data to a cloud platform. We can use local resources. So for example, a driver to deal with a sensor, or we could have some endpoint to collect or to write some data in another container. And in terms of performance, right now use containers that are around 1 kilobyte, quite heavy, but that's mostly due because we have multiple CBOR web tokens. They are equivalent to JSON web tokens, but in a more constrained expression. But even though there are um, more lightweight than JSON web tokens, they are still quite heavy. And that the size of the manifest will also depend on the number of endpoints that we authorize. And so this shows that in this context, it's even more important to make sure that we really give only the strictly required rights, because it will not only be better for security, but also it will really optimize the size of the manifest. Then in terms of RAM usage, well, we have done some tests on two types of devices. The first one is the most constrained one. It has only 256 kilobytes of RAM. And what we saw when we build an image with multiple containers, that we optimally, we think that what will run optimally, it will be with 3 containers, because the build, would represent 55% of the RAM usage if the network is deactivated. But now the entire build, if we activate the network, it, it we reach 90%, 99% of the RAM usage with only 2 containers. And so what that shows is that the network is really taking a lot of space, and that is um, really adds some constraint on IoT. But with a board that is a little bit bigger, well, there is no issue anymore whether the network is activated or not. We also did some tests while running some algorithms inside the container. So the first diagram you can see is running a tiny machine learning algorithm that was developed in the TinyPART project. And what we see is really that the main impact, it is at the loading. When we load a container. The reason is at that point, contrarily to WAMR, we are doing some checks. We are taking the manifest metadata and we are verifying it. So it means that we're verifying the tokens, signatures, we're verifying the endpoints, and that takes quite some time. And also we have a hash of the to calculate to guarantee the integrity of the code. So that takes a lot of time. There is also a little bit of impact on the runtime initialization, mostly because we are having some additional modules like the service, the adapters, the firewall to start. But then if you look at when we are using the functions to, for example, to apply machine learning to a model inside the container, well, there is not really a lot of impact. So really the impact, it's at the start, at the loading of the container. We also tried the same type of experiments when we have a container, but not running some purely mathematical functions. Uh, a container which is calling a native function. So here we developed a driver um, that does nothing, but it's just to measure the time to call this driver from the container. We see actually the same thing. Initialization of the runtime takes a lot of time. Loading the container takes a lot of time. But when we are calling, when we are doing some read writes, well, it's lower than 1 millisecond, just like when we are. And so if I continue on our side, we have our performance and memory usage, and we're planning to have some works on, for example, can we use better cryptography? And also, when we developed, we were really focused on functionality, but not really on code size optimization. That's something we could do in the future. We also would like to work on the root of trust. So, for example, this container, how can I anchor it really on a device and make sure that this container is really deployed on a specific device? We also have some work to do related to the consent collection. So what I mean by that is I am the recipient of a container. I would like to say that I'm not okay that the cartography service collects some data because maybe he could learn my address. And now we have the technical means to verify a manifest, but we need to work on the different aspects of how we collect this consent and how we translate them in a manifest. And what we saw already, that this is a challenge because depending on the order where you deploy containers, this has an impact. And also, we would like to see whether it's possible and to deploy multi-container service. What I mean by that is a service with multiple containers in a device or even on a fleet of device. So in terms of security, I will come back to the threat model table that we had previously, but now we filled it in with some components of the TinyPART toolset that we built in the project. And what we are seeing that, well, um, so for tampering, information disclosure, we have the tool that we presented today. So all of them are trying to prevent containers to be uh, changed um, either during their deployment or during the time where they are running. And for PIP and PU and Tiny Container as a Service, we also address elevation of privilege. Suit ensures that actually there is not an entity which is able to deploy a software instead of another one. So that's why we put it as addressing spoofing. And risk is a threat in privacy where we don't want users to not be aware of how their data are shared, how their data are collected. And that's a part, well, with Tiny Container as a Service, we did a first step to address this type of issue in the scenarios that we showed you. If we look more closely on the container threat model. So now we, as said previously, Suit, it's creating a secure tunnel to deploy uh, an image. So it will not guarantee, it will not address the fact that if it's given a malicious image by a legitimate entity, it's going to deliver it. But if we have a legitimate image and a legitimate entity, it will deliver it as is and it will not be changed. Um, and then, well, PIP and PU, Femto Container, and Tiny Container as a Service, both of them, they ensure that a container cannot attack another one or a container cannot attack the container runtime. So there are different types of needs from IoT device manufacturers, and that the TinyPART toolbox can help uh, uh, these actors to build their IoT with our tools. So if you want to know more, there are different websites from the contributors of the project. There is also some few articles that I put here. And finally, if you want to know more, we have an event on the 13th of December at IRSIC Lille. It is a Tiny Part seminar and also a PIP user club meeting. And so here is the program and the QR code if you want to register. So thank you very much for your attention.
Okay, wonderful. So let me just check. Okay. Yeah, wonderful. A super nice talk and many facets of cybersecurity. So thanks a lot for that. I have different access for question. Let's maybe start with a quite a general access, and that is when we talk now about products. So, who in this ecosystem would be the main stakeholders? So, who would have to adopt something, and what would they have to implement in order to have the Tiny Parts project as part of an ecosystem or as enabler of an ecosystem. So is it the IoT device providers? Is it some platform providers that are not existing yet? Is it the end users? So who would do something in order to adopt the platform? That
So,
one that
my
wants to answer
opinion,
can
there are
answer.
multiple stakeholders, and they're not necessarily interested by the entirety of the tool set, TinyPART tool set. So you could have some manufacturers that are only interested in PIP and PU, because maybe they want to maybe they have a lot of constraints in terms of size, maybe performance, and they would just want to have their native something very native and something really quite bare metal. But some of them maybe could be interested in PIP plus Riot, PIP plus Suite, um, but then if they don't have that many
I mean, am I the only one with
constraints,
audio issues, or
maybe they
do
could be
you?
using
No, it's cutting a bit with Chrystel.
uh,
Yeah,
Maybe she's on Wi-Fi.
well, tiny container uh, 2, because you saw that we're not as
Uh,
good in
so your connection is
performance
breaking a bit.
as PIP and PU. Or we could also have PIP and PU plus
And
femto containers
okay.
plus
So I think it also has just a huge
tiny
backlog, the audio.
tiny container as a service.
Okay. So if I
That
summarize what
could be
Chrystel was saying, it's the
done
different
too.
parts are relevant for different stakeholders in the ecosystem. Can Gilles
Mm,
or Emmanuel confirm?
so these aspects, these
I think
libraries,
Chrystel will, her audio will
they
still
can
come in for quite a while.
be added in
Because
a
even if I mute
build
her,
of an
it's
IoT
still
system.
coming.
So that would target mainly
But I think you can just talk. It will be okay, I guess, because we are
um,
louder than that is coming in the back. Because I also
IoT
don't have an audio
device
file
manufacturers.
just for her.
But if you consider tiny container as a service,
maybe
you saw
rejoin
that
or
there is
something.
an edge case
You could
Seems
try,
like
and
there's some
also
buffer that is like.
but I'm not. Maybe,
But like,
yeah,
I'm talking about like
platform.
Chrystel. Maybe she could rejoin or something.
yeah, might be a
So
good idea.
that would be more for an infrastructure
Okay,
So
good.
how about you ask your question again, and maybe I try to
Okay, so
answer it,
the
or
question is,
and maybe
well,
maybe
great. Yeah,
do.
let's do that. So the question is, let's just switch to me. So the question is, it's now a very cool toolbox, and it's very nice academic achievements, and it's all relevant parts. But at the same time, it's quite complex in the sense it has different assets for different parties. So if you would do now an analysis. Time to market and also what is needed to go to the market with this solution. So who would be the stakeholders that would have or would want to implement parts and which parts of the tiny parts framework in order to alleviate what to the market?
Yeah, so obviously, like maybe Orange would be a better place. I mean,
Mhm.
time to market, things like that is less of an academic for us. But so one thing that needs to be clear is it's not just a, let's say, slideware. It's actually tools that are already implemented, right? So and that can be combined in various ways. I think that's what
Krista said, yeah.
Chrystel was trying to say. And they can be combined as a software stack. So, for example, you can use Riot with or without this PIP memory management that is actually providing some additional guarantees. You can use it with or without suit updates. You can choose different types of. So it's kind of like a yeah, and it's a large variety of combinations that are possible. And again, these were, let's say, implemented already, and are can be combined in various ways already. So the question is like not about implementing this framework, is actually building on top of it, or starting to use it. And so I guess that any company who would be interested in managing remotely a fleet of devices that are basically low power devices based on microcontrollers could be interested in actually building on top of some combinations of these tools. And that's how we thought about that, and that's how we implemented it, and that's how what we demonstrate in our project is how to combine these things in various ways. So I think that would be like the easiest way to answer this question without going too much into.
Okay, no, that's good. Related to that, also on a more abstract level so far, what is the role of policymakers and of standardization for the success of the project?
I don't know if I dare to answer.
It's working out.
The sound
It's
is
working
okay?
fine.
Okay,
Yeah.
great. Well, there is an obvious response with suit, that it's already a standard. Now, for us, we are all on the tech side. On standardization, maybe what could be useful is to standardize some API for container management service, so that we could have some remote platform that could manage containers in the same way. Yeah, that's what I would answer today. But it's not for the project. For me, it's a success as it is.
Well, I mean, yeah, there's another way to do it. To look at this is, it's like this is a way for companies and to actually adapt to new standards and new regulations as they appear. Let's say you rolled out like this, service based on these boxes, and suddenly like a new GDPR 2.0 comes out, and like you have to, I don't know, obfuscate some part of the data that was not thought of before. And then, well, if you can just spit out a small containers that is going to be able to that you're going to be able to insert in your data pipeline on the device itself, suddenly, boom, you are actually compliant with the new regulation. And you can actually update that over the air securely, etc., with the toolbox. So I see it more like it's two ways. How to, yeah, you can see it like that also, like how to adapt to new regulations and standards.
Yeah, very very good answer. So my question was, I mean, you answered very well, because it's even another dimension. My question was rather into the direction, it's a cool project with super cool results, but in order to adapt to the market, standardization might be a next step, as you already started going. So, and so my question was rather to stimulate a bit that you talk about the role of the IETF, you work with the IETF in order to stimulate these different stakeholders in this ecosystem to at least think about such kind of solutions. But the retrofitting standards with the containers is also, of course, a super cool answer, because this is also a very nice feature that people are probably not even thinking of at the moment a lot. Okay, cool. You mentioned it already, the trust anchors. So if you now have an app ecosystem for containers, which could be the trust anchors in this ecosystem? Is it the developers themselves? Is it some app stores? Is it multiple app stores? Is it local site operators? Is it something totally different? Did you think about that already? Do you have some answers? Is it something collaborative, maybe using blockchain or something like that?
Okay, perhaps me. I think the first issue when we think about the way to deploy third-party software is the fact that in most of the microcontroller, we have no way to manage this in a safe way. So with PIP on executing place file system, we provide just the very first software component to allow to deploy safely third-party component. But it's clear that it's not enough to make a full-fledged ecosystem allowing to deploy on-demand service from third party. Today, this question remains open. Which kind of IoT device needs these services and why? And so I'm no real answer for about that, but I think we provide a way to manage it.
On my side, what I can say is that if I'm looking at the ecosystem right now, I would say that it's an emerging ecosystem. So I know at least two companies that provide container management services. They are very specialized on some specific type of board. There is also, during the summer, there was NXP that had an announcement that they have a partnership with another company to put containerization on microcontrollers. So for me, I think that's something that is coming, and we are also proof of it. I mean, we're not the only ones working on it, but there is still not an ecosystem, meaning that there is not yet an IoT deployed on it, and there's not yet a marketplace. But these are elements that I start seeing coming, and so for me, it's really the future, and we put a brick in this future. Um,
Okay, very, very good. Thanks a lot. So the domain you are looking at is Internet of Things or embedded controllers, which is typically a resource constrained domain, while resources being many things, CPU, memory, storage, bandwidth, and so on. Could you talk a bit about your experiences and the particularities of this domain? So what makes it especially easy or difficult to deploy such a solution in this domain, and which adaptations are necessary in order to succeed in this, well, I would say, rather challenging domain?
So are you talking about the fact that there are these resource constraints? Is that what you're and what are
Well, I'm talking about the domain you're implementing for is not a server farm in AWS. And so therefore you probably and also with all your backgrounds, you have to take into account certain design criteria and so on for such solutions, like low footprint in any terms and so on. And so if you could elaborate a little bit more into that direction to give the viewers a little bit an idea what is especially challenging in this domain, and how you could overcome these challenges successfully.
so I can start if you want that.
Mhm.
the experience on this, it did not start with this project. Actually, I had another project with PIP previously, and what we saw is that well, we were working. It was still a collaborative project, but we were working with another other companies in IoT. And the first thing that that was really not weird, but that's true. That occurred to me at that time is when we're talking about constrained IoTs, there are actually several words. There is the world of some people they talk about constrained IoT and they're talking about raspberries. And us, a raspberry, it would be a really luxurious place to deploy containers. I mean, Docker can run on a raspberry. It's very limited, but Docker can run on it. All our solutions that we develop in this project, it's really done for um, so small IoT devices. And we're not in the same world and we're not talking the same language. So actually for this project, it worked much better because we were in the same page on what is a constrained IoT device. So that's the first thing. And the other thing, in Orange, we did not we didn't make that much attention on optimization, but really what we did is that we always developed on the smallest IoT that we had, because like that, it forces us, if this thing it does not fit in it, it means that we need to reduce. If we had developed everything on the second IoT that I showed to you in the performance slide, well, we would have actually felt ourselves comfortable and we would have take more space. So I will let my colleagues respond.
The good thing with three people is three people can answer. They only have to coordinate who jumps in first. So Gilles, if you want to comment.
Yes, the issue is the fact that it needs some expertise to manage the footprint. So there is always way to deal with that, but it's basically the way Chrystel proposed is the best one. Just try to fit the scale, and you will face the real issue, and you have to deal with power consumption, with memory footprint, with, and then you will learn. But so this is a very specific part of software development. It's a specific environment here, for sure. There is in long time ago, I worked on various ways to make the step easier to do for a general purpose developer. We can imagine today we have way to support micro-Python in embedded system, to support with warmer JavaScript, or that's a good way. Nevertheless, the main issue remains. If you don't fit the scale, you have to learn to scale down your expectation of the software stack. You have to look inside your software development to say, is this really mandatory? Is this part really mandatory for me? And okay, that's the specificity of IoT development. So, it and it's not related to the fact that we are able to deploy post-iteration software or not. It's just the fact that we are looking for small device. It's not managed in the same way as a web server on a cloud, and we have to teach we have to learn to deal with that. And we have to teach how to deal with that. But there is various support for that, like various
Yeah.
language.
So let's say short answer is like that I could add is like you have to look at all the layers of the stack, like down to like what data structures you're using. Are you using like like whenever you start to have a complex program, like are you going to copy stuff over? Are you going to have a zero copy type of approach? and then you enter other types of problems like synchronization or security or whatever. But you have to look at all the basically like from the ground up. And at the network layer, that's the same for all network layers. So for the embedded software, for the network layers, you have to look at everything. So uh, even down to like the actual programming language you're using. Like for example, like right now we work a lot with embedded Rust
Mhm.
to try to have a, let's say, more solid base than C. But there, like the usual way to use Rust is to use like the standard library. But if you do that, then suddenly you have like a penalty in memory that's just so huge that you can't do it. So like basically you're doing away with some part of the, let's say, the facilities that are taken for granted by any sane people who are not working on this type of hardware. So you're really like you're looking at every aspect, every level of the stack, and this is what's a little bit difficult here, because you have to look at all that, and usually you can like stay at a rather high level, like very, let's say, a little bit further from the hardware than you're used to on these smaller devices. So it's really all encompassing.
Mhm. Okay, cool. Um, so I have two paths to go from here. Maybe the first one, really practical, hands-on. So if you now implement something, which is the tool chain that you use in order to optimize the software afterwards? So it doesn't have to be, if you want, it can be ultra specific if you want to name concrete tools like compiler performance monitoring tools and so on, but it can also be abstract. So if you deploy it, what do you do in order to measure the quality of the software artifact that you developed, and what is your quality metric? Is it size? Is it execution speed? Can you share a little bit that, having in mind that the people following might not be embedded systems developers, so just really don't overthink the answer. It's really just practically what happens once you deployed a piece of your software. How do you evaluate it, and to which metrics would you optimize it to?
So for on our side already, what we are looking, we don't have some really fancy tool to look at that beforehand. Basically, we're building, and already we see, will my IoT start, or will it crash immediately because I
Mhm.
already took too much size. Afterwards, if it's the case, what we also have uh, some some tests to because tiny container agent, it is a module of Riot, so we are looking at already the test unit tests from Riot, are they passing or not?
Mhm. Okay, that's good. Somebody wants to add something?
Yeah, so definitely like memory.
Mhm.
It's like for example, when we develop Riot, like whenever like a PR gets merged into the main branch, and you could look, okay, before after, like for the gazillion software configurations that we support in our CI, and we look at like, okay, what's the impact on memory, and if there are like some significant differences, you better be ready to actually explain yourself.
Yeah.
And if you don't have this discipline, then like very fast you end up with something that's just like like grown out of proportion. um, and for very specific cases, you also look at indeed like execution time. But so that's like very specific to, for example, the scheduler or something like that. If you're working on an actual library, like a crypto library, then you're going to obviously look at that in, let's say, like to be more central to your to your monitoring of quality. But one thing to note is also is that these quality levels, the thresholds or like the budgets within which you're working are like very stringent on one hand, but on the other hand, like depending on what you need to do, you know, some stuff you can afford. So uh, as long as you don't go beyond a threshold, for example, that if you can analyze your data faster than it comes in, you don't care if too much if like you analyze it like much faster or just like so there are these increments where like you can use a bit of common sense to not try to optimize to the death like the performance at that level and look at other aspects such as like the stuff still needs to be maintainable and flexible and whatnot. And there was some prior work on small OSs before Riot where they tried to optimize to the death other aspects. And in the end, well, the project died because actually they were using too exotic stuff that was too exotic and too that was underperforming on other aspects that are not like speed or memory size. And so you have to also keep that in mind.
And could you get a little bit in detail with the continuous integration part? So what are you testing with? Do you have certain setups you're running against in order to guarantee the software quality and the interoperability?
Functional solution like
for the container part. Can,
Yeah, my question is really, so as you develop and as the IoT is really and the embedded systems is a really heterogeneous environment, do you have a top 10 platform you run integration tests against? How do you work there?
on our side, we were more looking at the two platforms that we have, and sometimes we were using Fit IoT Lab to test whether our tiny container as a service fits on more IoT devices. That's the way we are doing it. And so a big shout out to Fit IoT Lab because it's really useful to do this type of experimentations and easily, rapidly.
Okay, cool. Gilles, you wanted to say something? Not. Okay, good. So the next question is software supply chain. Do you manage your software supply chain? Libraries do you use and so on? Do you use libraries or is it all from scratch? And if you do software supply chain management, what do you do? Do you have SBOMs or something like that? So software bill of material. Does it have an influence on your cybersecurity assessment of the software stack, or is it too far from the pilot? Such a question.
So right now on our side, we didn't really actively use SBOM. I would say that we have some common sense things that we're looking. So if we're looking at a library, we're looking its license. Is it compatible with our own open source license? For the development on our platform, on the cloud platform, we have a continuous integration and deployment chain. And in here, we're also looking at uh, dependencies and things like that. Now, something that could be interesting is if we have with the platform the capacity to compile code for others. For it could be interesting also to have a look at. We help multiple actors um, deploy these containers on one IoT device. And so what does it mean for the SBOM of this can we build an S bomb or an H bomb for this composite thing that we just built, and also the different stakeholders, what knowledge would they have of the other ones there? But because this could impact some elements, some policy that they have in their companies. So, but these are some open questions that could be tackled in the future.
Okay, very good. Time is advancing. Maybe a last question. So what, for each of you, what is the most important notion or feature of security by design for you? So what, because security by design is everything and nothing. I mean, a base understanding might be similar, but if you would have to tell somebody regarding your project, which is the best security by design feature, what would it be?
On my side, there is different aspects and there are different levels of proofs. So if you look at levels of proof, well, PIP-MPU is formally proven. There is a version of Riot where there has been some formally proofs. Femto containers, they worked on formally proofs. So I think formal proof is a very good part for me for security by design, because it's proving that what you claim that you are achieving is actually achieved. So for me, that's one part that is really interesting in this project.
Okay, cool.
But
thanks. Who wants to continue?
what about my colleagues?
Yeah, I think like um, this, this S bomb is probably something that's very fundamental. If you have no idea what's under the hood, like you're already like in a bad trouble, right? So, so the first thing is like know what you are eating, and like if you are eating people who also know what they're eating and recursively, then like at least you this is the base of everything, I would say. And so actually was using something like Riot and open source. You can actually, if even if we don't currently support like issue an SBOM, you can actually look into your make file and look like what modules are used, and you can actually figure out your SBOM to a large degree, right? And that's a huge strength of open source and something modular like Riot. And I think this is very maybe a little bit, even a little bit too basic of a comment, but yeah, well, if you don't have this, like whatever you built on top, you can't say anything about it.
Yeah, and I think this is a very important statement as well, because many people don't look under the hood, as we have seen with Log4j and others. So it's like, oh yeah, we just use it and nobody cares. So for me, this is really an important aspect of educating people. Gilles. I don't think we hear you. Yeah, we don't hear you. You don't have audio. Or I don't hear you at least.
Also, what I like to add is actually combination also of what is in your plate,
Knowledge. I
and
don't know.
the
Nobody
plate
heard me. Sorry.
what is in your plate is
Something
doing
wrong.
exactly what it's expected to do, is a very good one.
Yeah.
So S
Very good.
bombs and formal proofs would be really complementary.
And Gilles, we heard you now, it only had again this head of line blocking. So you said trust by knowledge. So it's probably related to what Chrystel was just saying. And I fully agree, because what you said, Chrystel, so having formal proofs, of course, is the strongest form of security by design, therefore, of course, super important. and at the same time to trust my knowledge. So looking into it and knowing what parts are in is important. And again, in a project that has to run on super resource limited entities, this could be a very good example for really exercising the thing, because you simply cannot rely on 2 million libraries. And so doing it right in such a context is super cool. And very good, very good. So yeah, as time evolved, I said we make 90 minutes. We did 90 minutes, so it was super cool. It was super nice, and I would still have lots of questions here on the sheet. So yeah, thank you very much for all the insights, for sharing, and for the people. Scroll back in the video for the QR code to join the event. The next edition and last edition for this year will be on the 13th of December. And we're at 2 o'clock again, and we'll have Sander van Linden from the University of Cambridge, and we'll go back to the fake news circle of topics that we have. And Sander will be talking about psychological inoculation against misinformation. And those of you watching, I will show you the trailer in a second. Thanks a lot. Everybody stay safe, and see you in roughly 2 weeks. Bye-bye.
Misinformation seems everywhere these days, and the talk will be relevant to anyone who's interested in the spread of misinformation. So I'll talk a little about what makes humans susceptible to believing in misinformation, and then looking at evidence-based interventions in terms of what we can do to counter it, including some of the problems with traditional debunking and a new concept known as pre-bunking or psychological inoculation, which is all about the idea of vaccinating people against misinformation by exposing them and refuting a weakened dose of it in advance.
Cher CyberCNI, pôle d'excellence région Bretagne. Au revoir et à la prochaine.